Hi, good day everyone. We are Group 4 and we will be discussing all about nitrogen industry. So we will be starting off with a brief background, then followed by history of the industry, then most common products, then it will be manufacturing processes. For the brief background, nitrogen is a non-metallic element with an atomic number of 7 and atomic weight of approximately 14.01 grams per mole. It is a colorless, odorless, and tasteless gas. Furthermore, nitrogen gas is one of the most prevalent elements present in the Earth's atmosphere. It is found in all living things and it has a variety of industrial applications which will be discussed later on. It is also the sixth most abundant element in the universe. Fixed nitrogen from the atmosphere is a key component of fertilizers that enable intensive agricultural production. The Earth's atmosphere is made up of around 78% nitrogen, 21% oxygen, 0.9% argon, and 0.1% other gases. These other gases that make up the remaining 0.1% includes small quantities of carbon dioxide, methane, water vapor, and neon. The atmosphere is the primary supply of nitrogen for commerce and industry. Many concepts of chemical and high-pressure processes were elucidated through the development of low-cost nitrogen fixation methods, and the subject of chemical engineering was developed. Prior to synthetic nitrogen fixation, the principal sources of agricultural nitrogen were different types of waste and manners, their breakdown products, and ammonium sulfate as a byproduct of coal making. Chilean saltpeter was derived from human and animal urine, and subsequently, ammonia recovered from coke manufacturing was essential. Synthetic ammonia and nitrates were then used in place of these natural resources. For the history of the nitrogen industry, who, when, and how it started. Joseph Priestley, a British clergyman and scientist, and Henry Cavendish, a British chemist, used electric sparks to dissolve nitrogen oxides in the air, producing nitrates and alkalis. Commercializing this technology has been difficult since considerable electrical energy is used inefficiently. Nitrogen has been fixed as a calcium cyanamide, but the procedure is prohibitively costly unless compounds leaving the cyanamide structure are produced. Other processes, such as thermal processing to mix oxides of nitrogen, cyanide formation, aluminum nitride formation, and decomposition to ammonia, show little commercial promise, although they are technically possible. Harbour and Nernst investigated the pressure-induced equilibrium of nitrogen and hydrogen to create ammonia and identified various acceptable catalysts. There was no high-pressure apparatus available, so they had to invent as they went. Harbour and Bosch also devised viable ways for producing affordable pure hydrogen and nitrogen. The obvious electrolysis of water for hydrogen synthesis and the distillation of liquid air for nitrogen production was too expensive, so they devised an alternative, more efficient techniques. By 1913, practical high-pressure ammonia production was achievable due to these collaborative efforts. This energy-intensive process has been significantly modified in recent years, resulting in prices that have not risen as quickly as energy prices in general. Major advancements have recently occurred and are continuing at a rapid rate.
Nitrogen is commonly used in various industries and applications, ranging from industrial processes to food preservation, electronics manufacturing, and chemical production. The first common product of nitrogen is the liquid nitrogen. Liquid nitrogen is often used to store and transport biological samples, vaccines, and other sensitive materials at extremely low temperatures and maintain their viability. Next is the nitrogen gas. Nitrogen gas is widely used to create an inert atmosphere in manufacturing process where oxygen can cause undesirable reactions or degradation. It is also found in the food industry for packaging perishable products. It displaces oxygen from the packaging, reducing spoilage and extending the shelf life of foods. For electronics manufacturing, nitrogen gas is used to prevent oxidation and ensures high-quality solder joints. Nitrogen gas is sometimes used to inflate vehicle tires due to its stable nature. It helps maintain proper tire pressure and reduces the risk of blowouts. Next is ammonia. Ammonia is a key ingredient in the production of nitrogen-based fertilizers. These fertilizers provide essential nutrients for plant growth and improve crop yields. It is also a building block for the synthesis of various chemicals, including explosive, dyes, pharmaceuticals, and cleaning agents. This chemical also serves as a refrigerant in industrial refrigeration system due to its high cooling capacity. Next is the nitric acid. Nitric acid is widely used in the manufacturing of various chemicals, including fertilizers, explosive, dyes, and it is also for metal etching, pickling, and cleaning processes in industries such as electronics, aerospace, and jewelry. Next is the nitrogen-based fire suppression systems. The nitrogen-based fire suppression systems, such as inert gas systems, use nitrogen gas to displace oxygen and suppress fires without leaving residue or damaging sensitive equipment. They are commonly used in areas where water or other extinguishing agents may cause additional damage.
Now for the manufacturing process of some major products of nitrogen, together with the discussion of their corresponding process flow diagrams. Next slide, please. So the main products made from ammonium nitrate is the fertilizer and explosives. The raw materials is ammonia and nitric acid. For the process made by reacting nitric acid made by oxidizing ammonia with ammonia. So the byproduct is nitrite. This is a highly toxic end product of ammonia oxidation that accumulates in the absence of a nitrite consuming process and is inhibitory to nitrifying in other bacteria. It is basically an accumulation during the process of oxidizing the ammonia. And next slide, please. Yeah. The use of explosives in mines and quarries provides a large and continuing market. Amatol is a mixture of TNT and granular ammonium nitrate. This is the major conventional military explosive. For the first equation, this is the result of the decomposition reaction where the ammonium nitrate rapidly and violently decomposes to form elemental nitrogen, as you can see. And under different conditions, like at 200 to 260 degrees Celsius, it is safely decomposed to form the anesthetic nitrous oxide. As can be seen in equation number 2, reaction equation number 2, this is the commercial method of the preparation. And then ammonium nitrate is made by reacting nitric acid with ammonia, which can be seen in equation 3. Next slide, please.
Okay, so now let's talk about the manufacturing process of ammonium nitrate. Several critical unit processes make ammonium nitrate, including the formation and concentration of solutions, the construction, finishing, screening, and coating of solids, and the bagging and bulk transportation of the finished products. Solutions may occasionally be combined for sale as liquid fertilizers. Nitric acid and ammonia combine to form ammonium nitrate. The resultant solution is concentrated to 97.5 to 98% in the final concentrator. A Pryling tower receives the concentration solution and a portion of it is also delivered to a slurry tank. The filler is mixed with the large and tiny particles in the slurry tank, along with the 97.5 ammonium nitrate solution released from the concentrator and scrubbing liquor to correct the mixture's moisture level. Next slide, please.
You can see here the process flow diagram of the manufacture process of the ammonium nitrate. Now, if the raw materials are properly proportioned and preheated, their action can be run continuously to produce molten ammonium nitrate containing very little water, 1 to 5%, which can be formed into small spheres or called prills by dropping the reaction product through a shot tower or into flakes by cooling it on belts or drums. By fluidized bed treatment, it is possible to obtain a dry granular material as product. So batch process have also been used, but the labor and equipment costs are prohibitive. Next slide, please. For urea, its main product is mostly fertilizers, and then its raw materials to be reacted together is ammonia and carbon dioxide. And then and other products that can be made through the process of thermal stripping of urea. There's plastics, adhesives, resins, textile anti-shrink agents, ion exchange resins. So you can see here some equations where urea can be prepared by introducing ammonia excess together with carbon dioxide at a pressure between 12 and 40 megapascals and a temperature between 150 and 250 degrees Celsius into a urea synthesis zone. The resulting urea formation can be presented best in the form of two consecutive reaction steps. In the first step, in equation 1, ammonium carbamate being formed according to the exothermic reaction. And then for the equation number 2, after which the ammonium carbamate formed is dehydrated in the second step, is to give urea according to the endothermic equilibrium reaction. Next slide, please.
Okay, so now let's talk about the manufacturing process of urea. A two-step procedure is used in the urea production plants. Ammonium carbamate, produced by the reaction of ammonia and carbon dioxide, is then dehydrated to produce urea. By evaporation or crystallization, the urea solution is concentrated, and the crystals can be melted to create pure urea in the form of pearls or granules. Urea is often produced at an ammonia plant since it has ammonia and as a product and carbon dioxide as a byproduct, both of which may be utilized directly to produce urea. Ammonia and carbon dioxide are the raw ingredients used in urea production. In an apparatus known as an reaction chamber, liquid ammonia is pumped while carbon dioxide is compressed and transferred. It is the core of the process since it was where the reaction occurs. For the first reaction to occur, the temperature and pressure must remain at 14 MPa and 170 to 190 degrees Celsius, respectively. Ammonia and carbon dioxide react in a way that is quite exothermic. The majority of the heat emitted is used in the form of process steam wherever it is needed. When carbon dioxide is present in excess, the conversion of the reactants to urea can increase and reach as high as 85% per pass. But because optimizing for the right temperature, pressure, and design is problematic in and of itself, per pass conversion is typically kept at around 50%. Over 99% of the materials are converted overall thanks to the recycling and unreacted elements. This lessens the impact on the environment. Next slide, please.
So the reaction product obtained in a urea synthesis solution substantially consisting of urea, water, unbound ammonia, and ammonium carbamate. The ammonium carbamate and the ammonia are removed from the solution or generally returned to the urea synthesis zone. A gas mixture is formed which consists of unconverted ammonia and carbon dioxide together with inert gases and the so-called reactor of gas. In a urea stripping plant, the decomposition of the ammonium carbamate that has not been converted into urea and the expulsion of the usual ammonia excess largely takes place at a pressure that is essentially almost equal to the pressure in the synthesis reactor. This decomposition and expulsion takes place in one or more strippers installed downstream of the reactor, possibly with the aid of a stripping gas such as, for example, carbon dioxide and or ammonia, and with the addition of heat. It is also possible to apply thermal stripping. Thermal stripping means that use is made exclusively of the supply of heat to decompose ammonium carbamate and remove the ammonia and carbon dioxide present from the urea solution. The gas stream leaving a thermal stripper contains ammonia and carbon dioxide, which are condensed in a high-pressure condenser and then returned to the urea synthesis zone. Next slide. So for the manufacture of the nitric acid, we have two types of processes. These are the single pressure process and the dual pressure process. Single pressure plants, commonly known as American or DuPont, and dual pressure systems called European. The single pressure plant has lower capital cost and produces more byproducts. Steam, the dual pressure unit, has a lower catalyst cost and a slightly higher yield. Currently, overall costs are almost exactly competitive. Next slide. I know, not joke lang. Balik. For its products, we have sodium nitrate, potassium nitrate, and cyanamide. For sodium nitrate, has both fertilizer and industrial uses. Fluxes, fireworks, pickling, heat treating mixes, tobacco additive, and etc. For potassium nitrate is manufactured in two ways: by reacting nitric acid with potassium chloride with a chlorine byproduct, and reacting sodium nitrate with potassium chloride and crystallizing out of salt. It is also can be used as a fertilizer. For cyanamide, At one time, it was used actually as an agricultural fertilizer, but its major importance came from its derivative, which is dicyandiamide. Its use has now sharply diminished until only one small plant remains. Its production is of considerable historical interest because a large plant was built to produce it at the end of World War I, but it was never successful commercially. And then next slide, please.
Okay, so the manufacturing process of nitric acid. Mineral acid nitric acid is quite corrosive. It has a colorless look that is comparable to water. However, older samples might develop a variety of hues of yellow due to the breakdown of nitrogen oxides in the water or the solubility of nitrogen dioxide in the water. The fertilizer, explosives, dye, fiber, plastic, fuel, and etching industries all use nitric acid extensively. About 68% nitric acid is present at the concentration that is most frequently used and sold on the market. Red fuming nitric acid is nitric acid with a 68 to 95% concentration. It is primarily utilized in the rocket fuel industry. And if the nitric acid concentration is above 95%, it is referred to as white fuming nitric acid. It is used mainly in the etching industry. The term aqua fortis for the nitric acid dates back to the ancient times when it was used to separate gold and silver. Ammonia was the primary raw material used in the Ostwald process to produce nitrogen. Nitric acid is created by a series of oxidation processes that begin with the oxidation of the ammonia. The other essential components are water and an oxygen source, usually air. To eliminate any impurities from the raw material, liquid nitrogen is first evaporated and transformed into a gaseous condition before passing through a filter. The warm compressed air is then sent through a filter to catch any contaminants. In the process, platinum or platinum-rhodium catalysts are utilized, with the rhodium content maintained at 10%. The cooler cools the gases coming out of the converter before the second chemical reaction step, which involves the oxidation of nitrogen monoxide to oxidize the nitrogen, predominantly nitrogen oxide and secondarily the nitrogen tetroxide. The nitrogen oxides are introduced into the absorption tower, which is continuously supplied with the air to increase the conversion of nitrogen monoxide to nitrogen oxides. Nitric acid is then produced from the absorption tower with a 60% concentration. The nitric acid concentration increases by 5% when a small amount, such as 2 degrees Celsius, reduces the temperature. This indicates that the absorption tower will release 65% of the nitric acid produced. Next slide, please.
Originally, the whole oxidation absorption or oxidation reabsorption process operated at atmospheric pressure. Such plants are expensive because the equipment is large. Atmospheric pressure cannot produce acids stronger than 50 to 55% nitric acid. Such plants are not now being considered. We have here a flowchart for the manufacture of 60% nitric acid from ammonia, DuPont high pressure 10 megapascals. Self-sustaining 225 tons per day unit. The expander turbine operates on the heat of the tail gas, essentially nitrogen. A high efficiency platinum filter collects platinum volatilized or eroded and is essential to economic operation. LLC, or the liquid level controller. F1 is feed intake. LIC is liquid level indicating controller. PIC is pressure indicating controller. TIC is the temperature indicating controller. And the TRC is the temperature recording controller. Next slide. Okay, now we have here a general overview of the raw materials and the major end product, which is the nitrogenous fertilizers. We have here raw materials: wood, lignite, coal, and others, hydrogen, and naphthalene, being reacted to ammonia, which has 82% nitrogen. So our most common nitrogenous fertilizers is ammonia, urea, and ammonium nitrate, and others. We have ammonia, which has the highest content of nitrogen. Okay, thank you.